All right, it is a 5 past the meeting time, so let's get started. So one of the things that we've been doing over the last, the second iteration of that is this PI sessions, or essentially programming interviews, and essentially the easy side of the question. So what we will be doing is walking through a bunch of essentially low complexity, low challenge programming questions, and I'm looking at people participating with solutions, and then we'll also try to think about how to think about these questions, how to problem solve, and things like that. So let's actually spend some time going through that. This is being run as a part of the SF Skillets, or the SDE skills in San Francisco, even though we've been doing it online. So a bunch of folks from all over the world are here in this conference. Just a 30-second preview. SDE Skills is an organization that's been essentially operating out of the Seattle area for the last almost like 9 years at this point of time. And we've been pretty active in and out. And for the last couple of years, we've been super active in the Seattle area. We have in-person meetups pretty much every weekend in one of the libraries. We're trying to kickstart something similar in the Bay Area. So if you're interested in volunteering, leading these sessions, please let me know. I can help you with the questions and sessions and likes. All right, so let's jump right in. So the questions are actually posted in the link, which is bit.ly skillets-pi-2, and it's essentially a link to the PDF. And today the focus is essentially Stack as a data structure. For folks who are not familiar with Stack, or not implicitly familiar with how stacks operate, is like, think of Stack as essentially how you can keep a stack of dishes, as it's commonly referred, or you can have like stack of books, right? The only thing that's accessible is the item or the book that is the top of the stack. You have other books in the bottom, but you really can't do anything till you get everything out of the top of the stack, right? So a typical stack operation is essentially, it's called a LIFO data structure, or last in, first out, because whatever you put in last is the first thing you have to take out. In general, most commonly, you can do only two operations. One is essentially push, which will add an element into the stack, and you can do pop, which removes an element from the stack. Now, it'll remove the top element from the stack, and none of the elements underneath are accessible. That is in a pure stack sense of the word. Now, there are two conditions that happen. One is when the stack is already full. In general, if you use like an array or something to implement a stack, you'll have a finite size, and it is quite likely that the stack is completely full. And when that happens, you essentially get what is called a stack overflow error. And the popular website Stack Overflow actually is just is kind of like named after this infamous error that happens when you are going into like some sort of like infinite depth recursion and things like that. Now, pop is essentially what happens when you pull something out. Now, what happens is that if you have nothing that has been pushed in, then there is a scenario of where you have nothing can be taken out. So that essentially results in what is called a stack underflow. Okay, so those are the two conditions. Now, there are some more like convenience operations that are allowed. Like one of the convenience operations is essentially a peek, which is the same as essentially just to look at the topmost element. And it is almost like a pop, but a peek might actually return the same stack underflow error if you try to do a peek on an empty stack. Okay, and there's always an isEmpty function, which lets you know if the stack is empty or not. And then you also have a size and a count. A size essentially returns the capacity of the stack, and the count actually returns the number of elements that are in the stack at this point of time. So that's kind of like a typical extra convenience function that you have, which will be used for multiple things. So in general, you're supposed to check if a stack is empty before you perform the pop operation, so that way you can avoid the underflow error. And you're supposed to check the count, and count is less than size, to make sure that you have capacity to push things. So that's kind of like a quick 4-minute rundown, 3-minute rundown of what Stack is all about. Any questions so far before we can start jumping into the actual questions? Any questions? So this is Amrit.
I have one question.
Go ahead, Vijay. Please go ahead. Was that Srikanth or Vijay? I couldn't hear.
Hey, Vivek, this is Srikanth. Actually,
hey, Srikanth, go ahead.
Yeah. Normally, this stack, normally in real-time scenarios, where we can use more predominantly, like normally in our applications, whenever we are doing the coding, so always we used to do some hash map, list, arrays, these types of data structures, right?
Mm-hmm.
So where predominantly we can use this stack, like any related to any job sort of things, any scheduler sort of things, there we can use this
Fantastic question. Is there anyone who wants to take a guess as to where would you typically use a stack? I mean, it's a data structure which makes sense, but where would you use it? Any thoughts? So one of the common places where you use stack is actually during recursion, right? When you're trying to calculate the same, like when you're calling the same function over and over again, the computer essentially puts things in a call stack, right? And that's how it knows that, like, for example, you're trying to calculate factorial of 7. The way you calculate factorial of 7 is essentially you want to calculate factorial of 6 and then multiply that with 7. In order to calculate factorial of 6, you have to calculate factorial of 5. Now, each of these elements, the factorial of 7 function goes into the call stack. Now, factorial of 6 function goes into the call stack. And as you go down to factorial of 1, which is actually hard-coded as 1, then that essentially pops the last function, which is essentially factorial of 2, right? And then that multiplies 2 with the 1 that you just got, and then it pops and keeps going back. So call stack is a very common scenario where you use it. Besides that, several algorithms actually require you to use a stack to do some things. Like, for example, a very common one is, one of the questions that we'll do today, like given an expression, tell me if it's a balanced expression or not. Like, do you have the right amount of left brackets and right amount of right brackets? The only way to kind of do that is using a stack. There are other problems that we typically solve around, like expression evaluation or traversing a tree, doing depth first search, where you either implicitly use the call stack or you explicitly define a stack or data structure, and then you go ahead and perform the operation. So there's a bunch of, like, stack is a fundamental data type, and it's a data structure which is actually used for a large number of like basic algorithms, and it's also fairly commonly used in a lot of other aspects. That make sense?
Yeah. Thanks, Vivek. Thanks.
All right, perfect. Any questions before we move in? Amrit, go ahead. You had a question.
Vivek, regarding the peak, is a peak a normal operation, or is it like recently got added?
A peak is just more of a it's been there, it's been around. I think if you look at the Java's implementation for stack, I think you'll see a peak. Most operations have it. You can easily implement it, whether you're using it as an array or whatever else. I mean, the first element is easily accessible, right? So implementing it is not a pain. So these are from a pure stack standpoint, it will only have push and pop, and that's it. And everything else you need to deal with. But peak is something that's it's useful in certain algorithms because you want to make sure that you can check before you pop. Otherwise, what happens is that you will have to deal with it as like pop it first and then push it back, which is kind of annoying for many algorithms.
Okay, thank you.
All right. So let's jump into the questions now. Okay. So the very first question that we have is essentially, is balanced expression? So the question is that you're given like 3 bracket types, and there could probably be a lot more. And your goal is essentially to tell me if the expression is properly balanced or not. And the definition for balanced, if for folks who are actually on the Etherpad, I'm on around line 21, and I'm actually on screen as well if you're looking at it. So an open bracket followed by a closed bracket is essentially a good expression. You could also have like 2 open brackets, 1 open bracket, 1 like curly brackets. Close this first, close this, close this, close this. So these are all like good expressions. Now this is a bad expression. right? Because you opened a normal parentheses and then you have closed it with a square bracket, and that's not allowed. Okay. So how would you actually make sure that an expression is balanced or not? Any thoughts?
Yeah, usually we will push when open bracket comes, and we will if any close bracket comes, whether it is a flower bracket or square bracket, we will see if the next popped element is of the similar similar bracket which is got opened, then we will pop it out. If something different one, then we'll treat that as a non-balanced expression.
Fantastic. Anybody has any questions on the algorithm? Do you think it will work? It may not work. Why? So let me rewrite your algorithm, Amrit, and see if it actually works, right? So first thing you did was you take one character, right? You're doing it character by character, and then if it is an open, then you push it in stack. Okay, and then if it is close, then pop from stack and compare. Okay,
correct,
for compatibility. Okay, if mismatch, then false. If underflow, you didn't say this, but let me add that. Right?
Yeah.
Is that what it is? Anyone can tell me what's wrong with this? Yeah, I can convert this to code as well, I assume, saying something like that. I'm just making some assumptions around what I'm writing as convenience functions, but I think you guys can probably figure out. Is that fine? Amrit, this is is this an algorithmic representation of what you said? I mean,
yes, that's what I guess.
Why is this wrong? Anyone can actually give me a test case where this will fail?
At the end, we have to check if all the characters are processed, like if the stack is empty.
Fantastic. What happens if this is the answer, right? If this is it? Will that work, Amrit? Thank you, Harika. That was like a good catch. Your code will return true, right?
Yes, it will not work.
That should work.
So after the for loop, I think we should check if the stack is
empty. So
yeah.
what I did was I just said return stack dot is empty. If the stack is empty, then return true. If the stack is not empty, then return false, right?
Yeah.
Okay. So this should work, right? So this kind of makes sense. Now, any questions? It's like a very straightforward question. There's nothing more complicated here. What is the size of the stack? Like, what is the maximum size that you think the stack will contain?
Length of the string.
Is it the length of the string?
Half length.
half of the length of the string. The worst case scenario is the half of the length of the string, right? You could have the first half being all opens and the next being all closed. While it doesn't change the algorithmic, like the space complexity, how can you actually do, how can you do better than this? How can you actually use fewer space? Let me actually change one part of the question and see if you can actually, do better. What if I told you that you don't have 3 different types of brackets, but you just had one? That's it. It's just this. Now, how will you do it? So this is not like a open set, closed set thing, right? So this is just like one element. That's it. So you can have multiple opens, multiple close, or you can have open, close, open, close, open, close, open, close, or something. Right? Things like that.
Hello?
Yeah, go ahead.
Yeah, so maybe we can just put a counter and count whenever you have an open, you put 1, and whenever you have a close, you subtract 1.
Fantastic. So in this particular case, if you actually end up using a stack, all you're trying to make sure is that the stack never underflows and that you end up with empty. So all you're caring about in that particular scenario is that the element in the stack, every element in the stack will only be the open bracket, and it will be exactly the same thing. There's no fun in doing that. All you have to do is keep count of the number of elements that would potentially be in the stack if you had used a stack, right? And that's about it. So in that particular case, all you have to do is that every time you see an open, then you just add 1 to the counter, and every time you see a close, you just subtract 1 from the counter, and you just make sure that the counter never becomes 0, and you also make sure that the counter returns to 0 at the end of the operation, and that's simple. So sometimes one of the tricks here is that the is balance expression is not always it's not always a stack question. Only if you're actually looking at specific types of brackets and things like that, multiple types of parentheses and brackets is when you need to figure that out. That was a good quick suggestion and solution. Thank you so much. All right, any questions on the first one? We can just jump to the second one. Okay. All right, so second question is essentially, let's assume that you have a stack where you're actually adding numbers, and in addition to adding the numbers, I want you to tell me what is the minimum value that is in the stack. Okay, and how would you do that?
Can you please give the example?
Sure. So let us say I add 6 to stack. Okay. What is the minimum value in the stack? 6. Right? If I add 7 to the stack, what is the minimum value in the stack?
6.
Still 6. If I add 5 in the stack, what is the minimum value? 5. If I add like 9, 8, 7, 7, 8, what is the minimum value in the stack? Still 5, right?
5, yeah.
Now I pop the 8. What is the minimum value in the stack?
5.
Okay. Now I add another 5. What is the minimum value in the stack? 5.
5.
If I pop this 5, minimum value is still 5. Pop the 7, minimum value is still 5. Pop the 7, pop the 8, pop the 9, still 5. Pop the 5, 6.
6.
Okay. So what is the minimum value in the stack? And one of the things that you can of course do is every time somebody is actually asking you to find the minimum value, you can always go and look at all the values in your stack like this and then say, oh, the minimum value is essentially 5, and you could do that, but that's going to take you a lot of time. All right. So how would you make sure that what is the minimum value? How would you find the minimum value quickly without actually having to go through the whole thing?
We keep a variable always every time we push push a value into the stack. We'll keep value into the temporary variable called minimum.
Got it. Fantastic suggestion. So let's see if that actually solves the problem. So now what I do is, so this is my test data. Okay. I pushed 6. What is the minimum value?
6.
6. I pushed 7. What's the minimum value? Still 6.
Still 6.
I pushed 5. What's the minimum value? 5.
5.
Okay. Now I pushed 9, 8, 7, 7. Still 5, right?
Yes.
Now I pushed 5. What's the minimum value? Still 5?
5.
Now I popped the 5. What's the minimum value?
Oh, this is a tricky. Yeah, here this will fail because I don't know the 6.
Yep, you don't know whether it was 6, so should I, like if this 5 hadn't happened, then I should be updating it to 6, and I don't know how to do that.
Yes.
Okay, that's a concern. So now how do you solve for this? Any suggestions?
We can have a temporary stack, like for every push we push a minimum element in other stack.
It's a fantastic. Somebody in the unnamed on the chat is also providing the same feedback. Thank you, Harika. So the concept is sound. So instead of actually storing the minimum value in a variable, you just store the minimum value in the stack along with it. Okay. So when you pop, you essentially pop. So this is when you say find minimum, you just use this minimum stack. So this is a stack that's just, and this is the real value stack. So now when you're adding elements, you add the element into the value stack as is. But then when you only add the value you add either you copy the previous minimum value as is in the min stack, or what you do is that you add the value as such. Right? What are the smallest values? It gets added. So if I have a 9, okay. So if I add a 9, then that what goes into the min stack is actually just a 2. Right. So that's about it. Now when you are actually popping a value out of this, you just pop from both sides, and that exactly achieves what you wanted to do, but recognizing the fact that it's not just one minimum value, but you have actually multiple minimum values, and you have to figure out how to get there, right? So does that make sense?
Yeah, but what if we don't have a space, if we have a space constraint?
What is that space complexity of having an additional stack? How many elements are you storing? It's order of n still, right? You are storing n elements. Now you're storing 2n elements. So it's O of n from a big O standpoint is still the same. Now there are other challenges or other items where you can actually there are other ways by which you can optimize this. So let's actually spend like a minute or two on the optimization front, right? So the optimization for this is this. So imagine you had the number 1 that comes up, and then you have like all these big numbers after that. That's it. Okay? And then there are like a million of these numbers, gigantic numbers. How many values will be in the min stack? 1, 1, 1, 1, 1, a million times, right? So one of the cheating that you can do is essentially to say that, so the algorithm that we said here was, if new value is smaller, then push new value, or replicate old value, right? That's what we were doing. You could actually avoid the replication of old value entirely, right? You could actually avoid this. And if you did that, then what will happen is your min stack in this example that we have will actually just have 1 just once. Okay. So when it comes to popping, you pop the big number. Since the big number is not the same as what you have here, do nothing. Just keep going, right? You only pop when the new value is actually smaller than the value that you have stored here. So in your previous example, the min stack would only contain 6, 5, and 2. That's it.
But what if I have a 1 in between? the 100. How would I know which one to pop?
That's a fantastic question. That's exactly the risk with this. So we talked about if the new value is smaller, right? What if it's not smaller, but what if it's equal? You will have to replicate. You have to copy.
So can't we just store, like stack the number itself, but only once, and keep a counter saying how many times I've seen it, I've stacked it, and each time I encounter that number, when I pop it, I just decrease it?
Sure, that also will work, because the only way it will actually happen is that you'll just have a replicated value, right? So yeah. So imagine you had 1, 1, 1, 1, 1, 5 times coming in. You can just store. That's a good extension to the same thing. So you could just keep a counter of saying how many times you saw 1. Okay, and let's assume that you had a 0 somewhere here. Then you'd actually say that I saw a 0 once.
Mm-hmm. Yeah.
Right? Fantastic. Who's speaking, by the way? I didn't catch your name.
Shalini.
Hey, Shalini. Does that make sense? I mean, this is, thank you. This is great suggestions, and these are the logical progression for the find minimum question. So the easiest way to do it is essentially to keep a complete parallel minimum stack and just use it. I think the very first idea that Amrit had of just using one value is the most obvious answer that you can jump to, but then you quickly realize that when you pop and you need to go back to a previous value, you don't have that data at all, and the only way you can keep that is essentially to maintain another stack so that you know where to go back to. An alternate approach would essentially be to kind of compress it, where you keep lower number of values, so you only add it, push only when there is a change. That is like a good way. But then the challenge with that is that what do you do when it's equal, and you don't have a good way of actually capturing that information. So for that, you have two options. One is if it's equal, also push it. Then you just deal with 2 stacks and you're done. Or the option that Shalini was providing was the one where you can add a counter along with it. And that way, because that only happens in equal case, right? So you just keep decrementing the counter, and once it's done, you can get rid of that. So these are the options that we have. Okay. Anyone wants to recommend? Is there a different approach or an option that you'd be thinking of? All right. So that is the second question. Any concerns about this question? It's a very commonly asked interview question. These are very simple, straightforward questions that actually test your knowledge of stacks, and it also tests your ability to reason and problem solve. And these are very simple questions. So the fact that you already know the answer will make it super simple for you to deal with it. But on the other hand, one of the things to note is that stack is just an abstract, like it's a data structure which is actually been put together. So you should be able to visualize that there are additional data elements along with it. So a stack is not just one entity, it's not just one number. You could have a pair of numbers. For example, the Shalini's example is that you'd actually have like a 1, 5, which could be a pair of numbers. And then you also have other options and other scenarios where you can have multiple elements or objects and things like that in the stack. Okay. In general, you are not permitted to look any beyond the first element or the topmost element of the stack. You cannot see what's coming beneath it. And that's pretty much like the fundamental principle that you cannot violate in a stack, is that you should not be able to read, access whatever is beneath the stack's top element. You should not even know what's there. I mean, the count you can keep count as an external variable and deal with it, but normally you don't even look at it. How would you implement a stack? What would be a good data structure to implement a stack on? Go ahead. What are the good data structures that you'll implement a stack with?
An array, maybe?
Linked list.
An array or a linked list? Harika, why do you think you said array, right? A linked list. Why do you think it's a linked list? Why a linked list?
linked list, we can increase or decrease the number of elements. I mean,
right?
The memory can be deallocated.
Correct. And where is the top of the stack?
Okay.
Linked list also, it is linear data structure, right?
Linked list is it's a linear data structure to a large extent. I mean, it's linear in terms of access, but from a memory standpoint, it can be all over the place. It's not. It is a pretty simple, straightforward, simple data type. But where is the top of the stack in a linked list?
Root.
Head.
Or the
At the
head.
tail?
Yeah.
Head or the tail? We have both. So which one? So I have a linked list which is like this: A points to B, points to C, points to D, points to E. Right? This is what I have. Okay, and E points to null. This is my stack. What is my head? A. What is my tail? E. In general, the last element, right? So now tell me what would be the top of the stack?
Head.
Head would be the top. You just insert in the beginning.
Yeah.
So
Correct.
insertion is constant time.
Insertion at the beginning is a constant time because all you're doing is you're just like setting the head as the new head, the new element, and then you're just attaching the previous linked list as is at the end, and you're done with it. Nothing stops you from saying that I will use the tail, but the problem is that once you remove an element from the tail, what do? How do you get to the next element? If I pop the E, right? If I kept a tail, then how do I know that I need to go to D? I don't have a link to D, right?
Mm-hmm.
Yep.
That becomes a challenge. So it cannot be a tail. It cannot be the tail.
Unless you use a doubly linked list, right?
In which case, it's not a head or tail in that case, right?
At that time, it will not even become stack.
You are only using the second link of the doubly linked list, in which case that is the head.
True.
Right? So I mean, in theory, that's good. When would you use an array? So linked list is a fantastic choice, but when would you use an array? And how would you use an array?
Yeah, if you know the size of the data element.
Yeah, like array list can be like the size is restricted for the array, right?
But what if you use something like an array list?
Array
then
list,
the size is not restricted.
Array list, the last element will be the top for the stack.
Mm-hmm. So in array, you have element 0, then you have element 1, element 2, element 3, and so on. Whatever is the last element that you have, you will actually keep an index of that, and that will be the top of the stack. Now, if it's a static array, like a integer array of like 100 elements or something, then you will make sure that you can only store 100 elements, and you will make sure that there's a stack overflow scenario happening there or not. If it's an array list, the challenge is that there is no stack overflow scenario because you can always add more elements to the array list in general. But the risk is that once an array list becomes big, it doesn't become small after that. Like even if you go down in terms of like if you add 1 million elements to the stack and then you remove 1 million elements from the stack, the memory usage does not go down for an array list because the array is still there and it's still occupying memory. Whereas in a linked list, the elements actually go away. But it's just a little bit more concepts on how you think about linked list and how it's actually stored. Okay? Any questions? Good work, all of you. I think we kind of like collectively figuring out what are the different aspects of stack and how to implement them. It's a fun exercise to actually implement the stack operations push and pop on your own, and then using an array and using a linked list and see how you can use that in some of these questions that we're talking about. Okay. All right. So let's do the third question. And how many of you are folks familiar with what Towers of Hanoi problem is? If not, let me just walk you through the question, like one quick iteration. So essentially, Towers of Hanoi is the way you have 3 stacks of like 3 rods or 3 towers, and then there are these huge gigantic disks where the disks are of different sizes. So a larger disk can never be put on top of a smaller disk. So the goal is essentially to move all these disks to 1, 2, 3 in this case, the green, the blue, and the red disks to C. That's what you should do. So the way you would do that, anyone wants to take a wager as to how to do this? How would I move the green, the blue, and the red to C without violating the rule? So let me actually say this is A, this is B, this is C. I have 3, 2, and 1 here. Okay. What's the first step? Like A has to either go to B or C. Those are the two choices. You guys want to pick which one? No idea. So let's pick one. So let me actually say I'm going to move it to B. Okay. What's my next step?
Move the second to the C.
Move the second to the C. Okay. Now what's my third step?
Move the 1 to C.
Yeah.
Move the 1 to C. Okay. There, done. So now that is essentially from B I have moved it to C. Then what do I do?
Move the 3 to B.
Yeah. Move the 3 to B. Okay. So I have done A to B. Then what do I do?
Move 1 to
A.
Move 1 to A. Okay.
Move 2 to B.
Then move the 2 to B. So which is essentially move C to B.
move 1 to maybe
B. Yeah. Move 1 to B, right? That's what I've done. So
yeah.
essentially I have moved everything from A to
B.
Correct? That's what I've done. How many steps did I take? 2, 3, 4, 5, 6, 7 steps. Right?
Yeah.
Now if I had to move this to C instead of B, all I had to do was just, I can swap this and say C wherever I said B and say B wherever I said C, right? That will work. How does this work? Now, is there a method to this madness? So one of the things that that we are following is that this actually follows the principles of stack, right? Because the only disk you can access is the topmost disk, right? You can't access disk 2, you can't access disk 3. And the only other element is that when you're pushing, the push operation actually has a constraint, which actually tells you that you cannot push a greater number than what can be peaked. Okay? I mean, if the stack is empty, then you can put whatever you want. But otherwise, if the stack has some value, the top value that you have in the stack is the one that the newer disk has to be smaller than that.
Yeah.
So what do you guys think? How do you actually how do you do this? So this is a recursive problem. So how do we do this? Any thoughts? Think of it as a recursive subproblem. So let's assume that I have 100 disks, okay, that I need to move from A to B. That's what I need to do, okay. And this is a function. So you have a function that is essentially move stack from a source location to a destination. So in this case, the source is A, and the destination is essentially B, and using what I'm going to call it as a temporary disk, temporary stack, location as C. This is what I have, okay? And I am actually moving essentially N is 100 in this case. The values in the brackets are actually function parameter values. Okay, that's what I want to do. So let's assume you have this function, right? So in theory, what I want to do is somehow, magically, which is what you did, is somehow I want to be able to move 99 disks from A to C somehow. Let's say you could do that from the source to temp, then you just move single disk from A to B, in this case like to destination, and then you just move the 99 disks from the temp to destination. Would that work? Assuming you know how to move 99 disks, right? How would you move 99 disks?
Yeah, this one maybe we need to run in the recursive.
Yeah. Just use the recursion. That's it, right? So now when you're moving this 99 disks, right, all you're doing is this is essentially move stack, where the source is essentially the source, still the source. The destination is the temp. And while we are at it, you can always use the destination as the spare. And you're moving n-1 disks. This is going to be a little bit confusing, so let me write this. From temp to destination using the source as the stack. Okay? And that's it. This actually should, and -1 of course, right? There's only one condition, is saying do nothing. If there's no disks to move, do nothing. Okay. So let's find out how this works, right? So what was our goal? Our goal was to move 3 disks from A to B using C as a spare. Okay. What is the first? What's the first step? You want to move 2 disks from A to C using B as a stack. Correct? How do you do that? You want to move 1 disk from So how do you do? You want to move 1 disk from, in order to move 2 disks from A to C, you need to move 1 disk from A to B using C as the temp. Okay, and this is simply move single disk. Okay. Then what do you do? Move single disk from A to B. No, A to C. And then you need to move 1 stack from B to source, temp, destination. So move from destination, which is C, from temp is B, sorry, to
C.
Destination, which is C, using A as the spare in this case. Okay, so this is what happens. So what this does is that if you want to move 3 disks from A to B, then you first have to move 2 disks from A to C. To move 2 disks from A to C, you'll have to first move 1 disk from A to B, which you can do. Once you've moved disk number 1 from A to B, then you move disk number 2 from A to C. Then you now need to move the stack of just 1 disk from B back to C, B to C, right? So that finishes up, and that's what this is. Now once you're done with this, that takes care of this guy. So now you have 3 still left with A at this point of time, right? 3 is on A and C has 1 and 2. Okay. Now what you're doing is you're just doing a second step of this operation, which is move single. disk number 3 from A to B. Okay, at this point 3 is on B, and your C has 1 and 2. Third step is essentially move 2 disks from C to B using A as the temporary spare. This will repeat the same thing that you have here with the ABCs being stepped out. And that should actually get you the full thing. Anyone wants to try coding this? That's it actually. That is the code. We already have the code here.
Yeah.
You don't need the n. You don't use it at all for anything. But you need to keep track of the n because you need to know how many disks have happened, right? So you need to just count. And that's it. And when you're printing, the move stack actually does nothing. The move single disk is the activity. So this is what you're printing. Something like that. And that's it. You're moving this number and this should print whatever we just talked about. Any questions? Any questions at all? Towers of Hanoi seems interesting.
Are they not stacks, those parameters?
No, they're just characters. Just the letters, that's it, right? It's just I mean, you don't need the stack, right? You just need to know which tower, that's it.
Okay.
I mean, you could have these as actual stack objects, and then the move is essentially pop from one of the stacks and push into the other stack, right?
Yeah, that's what.
You could do that. And that actually is a meaningful way of actually testing, getting this thing going. There is another variant of Towers of Hanoi that I was actually looking at, which is actually fun, which is if you go to the Wikipedia entry for Towers of Hanoi, there is an entry where you actually start like this, where you have white, like black and white towers, like the first stick starts with, like, a disk 4 of black, disk 3 of white, black, and black, white in the peg B. And the same rules apply. At no point of time you can actually have a bigger disk be placed on top of a smaller one. But your goal is to start from this combination and end with this combination of where all the white disks are in one place and all the black disks are in another place. Okay? Not an easy recursive problem to solve, but it's actually a fun thing to think about. If you've actually worked on Towers of Hanoi, then you would know. Okay. All right.
Yeah.
Anyway, so any questions on stack? The goal of this exercise is to kind of keep it super simple, pretty straightforward, and then we just walk through the data structure and a few questions to help us practice. Any thoughts, any questions?
So regarding the find min problem, the solution I gave has definitely limitation. So do you consider that as a brute force solution? Because it's not complete solution.
It's not a solution at all. It doesn't solve it, right? And the fact that you immediately recognize when there's a problem is a good thing. But that won't be a solid solution. So that's not a brute force solution. The brute force solution, the worst case brute force solution would be where you were to say that I'll go look at the stack again, I look at every element in the stack. I'm going to implement it as an array or a linked list, but I will go through every element in my stack and then use that to figure out what the smallest element is. That would be probably the brute force. Even storing all the elements in another stack is also not very space efficient.
Okay.
Even though it's O of n. Okay. All right. Any other questions? All right. Awesome. So let me pause the recording here, and then I'm open for more questions if folks want.